All right, everyone, let's get started. So from my understanding, Lab 1 went smoothly. That's good. That means that you guys got a good experience in CSCE 212. You have a strong background in assembly, or could mean the TAs are really good and they're doing a good job answering questions, or both. So today we're going to switch into the hardware part of the class. And we're going to talk about logic circuits and SystemVerilog. So in, actually that should say CSCE 211 review. Actually, in CSCE 211, you guys designed some logic circuits, or you should have anyway. And you might not have realized it at the time, but you used three different ways to design the circuits. You used, you designed their behavior with Boolean logic expressions, right? You guys remember that? That's a behavioral description. It defines what the circuit is supposed to be doing, its functionality, its behavior. And then you also design circuits structurally by creating a schematic of digital logic gates. So you should be familiar with that. And of course, you can take the behavioral description and you can translate that directly into a circuit of logic gates that performs that behavior. But the structural description doesn't really say much about how you build the circuit. It's really just a set of components and the way in which they're interconnected, right? So in order to actually build something, you then have to design it physically, which you guys should have also done using breadboards and logic chips, TTL chips. And so you had to decide, in this case, for each one of the gates in the structural description, you had to allocate one of the slots on one of these chips for each one of those gates and then plug the corresponding wires in, right? So essentially, you guys really followed the same process that we're going to use in this class, except we're going to use a CAD-based approach to automate most of this stuff. Okay? So, you know, this is just another kind of way of showing that. You did a Boolean logic. You probably wrote that out by hand. You might have even drawn the logic gates in by hand, although you might have used Logic Sim as another approach, a free CAD tool. And then you might have minimized it with Carnot maps, and then you drew out the schematic, and then, like I said, at some point you built the circuit on a breadboard. You probably thought to yourself, though, that this is not a practical way to design chips, right? Because this is a very low density and very error-prone way to do digital logic design, and it's not scalable. So I just thought it was a fun mental exercise to think about what it would take in terms of this design style to build a modern CPU. So if you take a modern CPU, it's going to have at least 250 million gates on it, and that's not even including the cache. That's just the logic, the gates. And so something like that, I calculated, would take 8 million breadboards, which would be over 1,000 miles long. So that wouldn't be, you know, and even if you could design something like that, imagine trying to debug it and to reuse parts of it for the next generation of chip. It wouldn't be practical. So these are the challenges that CAD tools are trying to address, or sometimes they're called EDA tools, electronic design automation. So in this class, we're going to use the same three styles: behavioral, structural, and physical. But the behavioral description is going to be specified in a high-level language called SystemVerilog. That's going to be similar to writing, you know, at least in the way that you actually enter your design. It'll be like writing any high-level code, like in Java or Python. And then we're going to use CAD tools to take that and to compile it, or actually it's called synthesize that description into a structural design. Now, with the kind of designs we're doing in class, there's different versions of the structural design. The one version of the structural design is just a gate level net list. This is a net list. It's a schematic of gates. So this is one way you can represent the schematic. This is called a pre-mapping schematic. However, we are going to be targeting FPGAs which have that they implement the lookup table, the gates rather, using lookup tables, right? Using 7 input lookup tables. So at some point you're going to have to take these gates, and you have to map them into the resources available on the FPGA. And once you do that, you have a post-mapping netlist that looks the same. The only difference is instead of the blocks in this block diagram being logic gates, they're actually just blocks that represent physical components that are available on the FPGA. And then when you're ready to deploy it in the field, you go through a process called place and route, where you take each one of these blocks and you decide, much like you did with the breadboards, you decide where you want to put each one of these blocks on a physical substrate of some kind. In this case, it's an FPGA, so there's these empty slots where you can allocate each one of these guys. Now, this is challenging computationally because you want to do it in a way that makes the design fast. So things that are connected need to be close together, essentially. And then you have to allocate, not only the actual gates have to be allocated, but the wires too. Yes? Is there any algorithm which can optimize this process of placing things and wiring them? Well, it depends what you mean by optimize. It's the algorithm that they use simulated annealing, which is essentially just it's random selection. They just randomly allocate it, and if that random allocation is better than the previous attempt, and they keep it. Otherwise, they throw it away and try again. And that's essentially basically the process they use. It's a little bit more complicated than that, but you can't do it optimally. So the idea is to just try to achieve a good mapping. So this is not very. Unfortunately, this figure is not very descriptive. This is actually a screenshot of the tool that we're going to be using called Quartus. And I've zoomed in on the actual fabric of the FPGA. And basically, every one of these boxes is a slot, and then these smaller boxes are also slots, and these are slots for I/O pins. And you can see that just a few of them are filled in, like darker blue, and those are the ones that I've taken this design and I've allocated on that array, right? So we still have this idea of behavioral, structural, and physical. Now it's a little bit of a misnomer though, because it turns out that when you write code in SystemVerilog, you write some behavioral code, but a lot of the code you write is actually structural. So you're actually building a structure, like you're instancing and connecting modules, but you're doing it in SystemVerilog. Typically in a SystemVerilog design, it's hierarchical. So you've got designs that are comprised of smaller designs, and those smaller designs are comprised of smaller yet designs. But then at the very bottom, at the leaf nodes, is where you have your behavioral code. So typically, most of the code you write is going to be a textual description of this kind of design. You're kind of instead of drawing a schematic, you're going to be writing it into a code, and then sometimes you'll write some behavioral code, and it gets mixed in together. But there's basically two styles of SystemVerilog: structural and behavioral. So you'll see those terms come up a lot. Structural just means schematic, block diagram, and behavioral means something logic does, which ultimately boils down to Boolean logic. Okay, so you might be wondering about this SystemVerilog. The syntax looks similar to Java, but it's the way that you write it is a lot different, as you'll find. So I mentioned SystemVerilog is a type of hardware description language, or HDL. There's mainly two HDLs that are the most popular by far: SystemVerilog or SystemVerilog, and VHDL. There's some other ones too. They tend to come and go, but none of them have had the longevity of SystemVerilog, Verilog, and VHDL. And I'll talk more about those in a minute. But basically, what's the idea behind an HDL? What is the premise? The premise is that you're leveraging. There's three concepts: abstraction, hierarchy, and regularity. And these are basically all the same thing, really. Abstraction just means, as I mentioned earlier, that you build increasingly complex designs by building on top of less complex designs, right? So for example, you'll have your architecture is built from a microarchitecture. I mentioned those terms in the last lecture. So the architecture, which is just basically a block, like a kind of a black box as CPU, it'll run code. If you drill down into that and you see how it works internally, it's a microarchitecture, which is digital components connected together, data paths. And then that is, each one of those blocks that make up the microarchitecture is a logic block, and then if you drill in there, you eventually get down to where you just have digital logic gates, essentially. So that's the idea of abstraction. And then hierarchy is pretty much the same idea. It's that you might be thinking, well, wait a minute, you said that CPU is 250 million gates. Does that mean I'm writing a 250 million line SystemVerilog code to build that? Well, no, it's not nearly that complex, because if you look at each individual SystemVerilog file, they're generally pretty short. But there's a hierarchy. They instance other modules, and then you go inside those modules, and there's other modules. And because of the way the hierarchy is arranged, when you go to put it on an FPGA or an ASIC, you flatten the hierarchy. You take all that. The hierarchy is there just for design purposes. But ultimately, when that hierarchy gets flattened and all the levels come out of it, and it's just squished down to a big pile of gates and wires, then it becomes this enormous design that forms the enormously complex design you'll have in a modern CPU or GPU. But the designs are meant to be as simple as possible, so you can debug them and you can expand them and you can read them, basically. So the idea behind hierarchy is that you want to try to make your designs readable. So what that means for you is that when you're writing code, you could put, for example, your whole CPU in one giant file if you want to, which is actually the way I do it, but that's only because these CPUs are not that complicated. Or you could do what someone like Charles would do, and you would subdivide the design into smaller files that are arranged in a hierarchy. So you would modularize it basically more. And so, but that's up to you as a designer. That kind of goes into the sort of practices and habits you have when you write this code, right? But ideally, you want to try to take advantage of hierarchy. Of course, you could go overboard. You can have modules with one line of code in them, and then you end up with hundreds of modules, and it gets hard to track things down. But that's something that this idea of hierarchy is there as a design convenience, basically. But ultimately, when you deploy this thing, it gets crushed down into a big, massive sea of wires, basically. And then regularity is the idea that you want to try to, in this hierarchy, you want to try to minimize the number of unique designs, and then you can create arrays of them, for instance. So in the case of a CPU, so here's an example of a CPU hierarchy. A CPU has processor cores. You have a CPU on the top level. And I'll say that word a lot, by the way, top level. Top level is kind of the starting point of your design. It's kind of the design you're testing or the design you're shipping to customers. That's the top level. Whenever you synthesize a design or simulate it, you have to specify the top level. So the top level, in this case, I have the CPU at the top. If you drill in there and you go into it, you see that there's multiple processors. Each processor has functional units and a register file. If you go inside a functional unit, that might be a floating point adder. If you drill in there, it may have a comparator, a shifter, and adder inside. If you drill inside the adder, you have full adders, right, for instance. So you'll notice that what you want to try to do is exploit regularity. You have these full adders. They're just a bunch of full adders inside of one module. So even though there's only two modules that someone designed for this, you end up with this you can still leverage this to get a complex design. Like here, you've got multiple functional units that make up inside the processor, right? So my point here is that you want to try to create modules that can be reused as often as possible. That's essentially what I'm trying to say. Okay, so and that's the regularity. Okay, so let's talk more specifically about logic circuits. So you guys have, as I mentioned in 211, you designed some digital logic circuits. I think probably all you guys have used, though, are these digital logic gates, like a NOT gate or a buffer, and you looked at the symbol and the truth table, and you know that there's inputs and there's outputs. Now the problem here, and you might be thinking this already, when you write code in a high-level language like Python or Java, it has sequential semantics, meaning that when you write the code, you imagine that the processor is kind of always running through, it's always on like one line of code at one time, right? It kind of runs through and it kind of follows loops and if statements, and there's like a flow that goes through, and every line of code is executed in order, essentially, or in the order that you've set it up to be executed in terms of your loops and procedure calls and if statements and that kind of stuff. The problem is that you can't build something, that's not how hardware works. Hardware is inherently concurrent. You've got these wires, and if you have an input and an output of a gate, anytime the input changes, the output is going to be updated as soon as the electrical signals propagate through the gate, right? which basically involves charging or discharging a capacitor ultimately. So and every gate is concurrent. Every gate is operating without, generally logic circuits on a chip are all operating concurrently. There's no order there, right? So the problem is when you write SystemVerilog, in general, now there's a couple exceptions, but in general, the order of the lines of your code don't matter. You could take a SystemVerilog code and scramble the lines and it won't make any difference because all the lines are essentially executing at the same time. There's no notion of where the CPU is as it executes the program. Now there is something called processes, which follow sequential semantics internally, but then when they are synthesized into gates, they become, that process by itself becomes concurrent with everything else in your design. So you'll see, a lot of times you'll hear me mention that, the order of lines of the program make no difference in Verilog. Okay, so you guys remember that there's a AND gate, 2 input gates, and so forth, 3 input gates. You guys looked at. So in this case, this is the structure or the symbol of the gate. You can think of this as a structure, especially if it's connected to other gates. And then this is the truth table. In this case, is the behavior. And of course, you could represent this truth table as Boolean logic if you wanted to. And those are just 2 different ways to represent the behavior of the gate. And basically, that's what behavior is. Really, ultimately, it's essentially truth tables. When it comes down to it, you're dealing with truth tables or Boolean logic, or in the case of sequential logic, it's state machines, which I know you guys don't cover that in 211, but we will be covering that in this class. Okay, so just to define this, a logic circuit is comprised of a set of inputs, a set of outputs, a functional specification, which it's basically its internal behavior, and then the timing specification. We will talk a lot about the timing specification at the end of the semester. We're not going to worry about that too much in the first part of the course where you're going to be building stuff on the FPGAs, but I'm going to talk more about timing closure towards the end, kind of as a concept. So right now, you can just think of this as having inputs, outputs, and some kind of functional spec. So basically, in SystemVerilog, every file you write has a module in it, and that module is this. It's got the first line of the file is the inputs and the outputs, and then inside there it's the functional specification. And then those modules, inside the module, you can instance other modules, which is where you get your hierarchy from. But every file in SystemVerilog is basically a description of a single logic circuit. And then, as I mentioned, and this is basically what I just said, if you take that logic circuit and you look inside of it, you'll see potentially things like internal wires, right, that are hidden, that are abstracted away inside. Other modules that are implemented in there. Hopefully, you don't have too many unique modules. So if you have a lot of the same, like if you have an array of modules, like an array of full adders to make an adder, that's an example of regularity. But from the top level, it's just kind of like a class in Java. There's an interface that the user has, which are the inputs and the outputs. Okay, so that's kind of giving you an idea how these files are, how they're arranged. So I mentioned there's this notion of combinational logic and sequential logic. I want to mention this now. I'll be talking more about this later. Combinational logic is logic that's where the behavior is memoryless. So the outputs are just a function of the inputs. And so lab 2, which I've already got posted, will have you just making combinational logic, but you can still put that on the FPGA. And then once we get to lab 3, we're going to be building the first version of our RISC CPU. Then we'll have sequential logic in there where there's memory inside there in the form of RAM and registers. Okay, but right now in lab 2, we're going to focus on, and in the first part of this lecture, we're going to focus on combinational logic. So again, the difference is combinational logic has no memory, sequential logic does. Now, is there a different syntax, or is there a keyword that you have to put into SystemVerilog to define that? No, it just all depends on how you write the SystemVerilog module. It's the same way, like earlier I mentioned that there's this distinction between structural Verilog and behavioral Verilog. But again, that just all depends on, there's no formal way that you specify a module as being structural, which is the schematic, or behavioral, which is the truth table. You basically just, depending on which idioms you use inside define what that is. And you can mix them together too. You guys with me? So you can have one module that has some combinational logic and some sequential logic in it, as well as some structural HDL, which is just an arrangement of modules connected, and some behavioral HDL, which could be essentially some Boolean logic. Okay, so we're going to look at a lot of these. Schematics. And you might say, wait a second, I thought you said SystemVerilog doesn't have schematics. You can do schematics, but you have to write them into the language using the syntax. Yeah, but so a lot of the designs, the way that we run this course is, I will give you schematics that are graphical, and then your job is to then translate those into SystemVerilog, essentially. And in the process, you learn how to conceptualize designs in SystemVerilog, right? So, but you're going to see a lot of schematics because this is how we're going to convey to you what the designs look like. And you guys have already seen this in 2.12 when you studied the MIPS CPU. There's a whole chapter in that book, chapter 4, where they show you the design of the MIPS CPU as a structure, as a big block diagram. You have the multiplexers and register file and ALU, and there's all these blocks that are interconnected with wires. So you're going to see a lot of that. You have to get used to seeing those and interpreting those. So there's an example of one there. There's a few rules. I mean, it's not a formal thing usually, but there's a few rules that you should follow whenever you make a schematic. Generally speaking, you try to put the inputs on the left, although I don't always follow that rule. You should try to keep the inputs on the left and the outputs on the right, so there's this kind of left to right flow of data. And then straight wires are best, but the problem is that anyone that's tried to make a schematic, that it's hard to always have straight wires in it. And this is the thing that can be a little confusing when these designs get more complex, and you try to exploit. Again, you try to exploit hierarchy and regularity to try to keep these things simple. But as you guys know, when you looked at the CPU in 2.12, sometimes the block diagrams get turned into a rat's nest, right? So they get complicated sometimes. But when you're looking at all the wires flowing all over the place, whenever you have wires that are in a T-junction like this, you have to assume that they're connected. And but if they cross, they're not connected, unless you put a dot there to specify they're connected. Now you might say, well, why wouldn't you just assume they're connected if they cross? Well, it's because oftentimes you're going to have a lot of wires in these diagrams, and sometimes they have to cross. And so you don't need the dot if there's a T, because why else would you have these unless, why else would you have them arranged like this unless they were supposed to be connected? But if there's a cross, again, you have to assume first they're not connected unless there's a dot there. Okay, so keep that in mind. Okay, so the other thing about SystemVerilog is that, in any HDL, is that you're dealing with just binary data. Everything is just an array of bits, generally speaking. Now, there is some ways that you can do some modeling and some simulation, test benches and stuff where you can actually implement other data types. But in this class, we're going to focus on SystemVerilog that is synthesizable, meaning that it can be converted into hardware, right? And so we're going to stick to using all just binary data types. So all of you can have variables and inputs and outputs, but it's all assumed that they're just binary signals with a certain width, right? However, the problem is that you can't just have 0 and 1, because when you run simulations, when you're testing your design in simulation before you deploy it on an FPGA, the simulator has to have a way to convey to you, the designer, when something is kind of goofy or off. And so the way it does that is through additional, instead of 0 and 1, there's some additional values that the signals can take on. Either in totality, like if you have a 4-bit signal, you can have all 4 the same, or you can have like a 4-bit signal and you got some 1s and 0s in there, but you may also have some of these special characters. And one of them, and the one that you really need to know about, is contention, which is where if you have 2 drivers, you have 2 blocks of logic inside of one module or it doesn't even have to be in one module technically, that could happen across the hierarchy. But if you have 2 pieces of logic that are trying to set this different values to the same physical wire, or what would be realized as a wire in the deployed design, In other words, you have one piece of logic that's trying to put a 0 and the other one's trying to put a 1 on there, right? We call that double driving. It's essentially you've got one transistor trying to pull up to 1 and another one trying to pull down to 0. And what you end up with there is a low impedance path between the power supply and the ground. And in practice, what will happen is that you'll end up with a voltage value on there that's going to be between 0 and 1, right? So if you're on a 2-volt device, for instance, you'll have a voltage on that signal, it could be around 1 volt, like halfway in between, which is called is in the forbidden zone. You don't want to have voltages that are, not close to ground or close to the power supply in a binary system. So now you might say, why are you bringing this up? Who in the heck would ever do that? Well, it turns out that it's very easy to make this mistake in Verilog, because all of the wires, so you don't actually draw wires in Verilog. You actually just create symbolic names of something that represents a wire or a voltage at some point in the system. And then it's very easy then to just set that variable at 2 different spots in your code. So this comes up quite a bit. Now, if you were to synthesize something like that, you'd get an error. But if it didn't error out, then you would essentially be introducing a short circuit or a potential short circuit, assuming, in order for it to be a short circuit, you'd have to have two, you'd have to have someone trying to set it to 0 and someone trying to set it to 1. But you could introduce a potential short circuit, which could sink a lot of current and heat up the chip and possibly cause physical damage to your chip. But when you simulate, and this is before you try to synthesize, the simulator will let you do that. But when you do it, you'll see these X's, right, red X's, and that just means you have contention. However, the problem is Verilog has, unlike VHDL, Verilog only has it has limited number of values. So obviously 0 is 1 and 1 is 1 and X is 1, as I mentioned. However, what happens if, for example, you have a register that is not initialized, right? Now, in real life, it would just come up as a random value, but in Verilog, it uses that same X, which means don't know or undefined. VHDL has a U it uses for that, so VHDL is a little nicer in that sense. Likewise, what if you want to set a value to don't care? You guys remember don't cares from 211? Don't cares basically means, I don't care what this is, you can use this don't care to optimize the logic. Well, don't care is also an X. So the problem is that X usually means contention, but it can mean something else depending on the context, so watch out for that. So this is this is showing what can happen if you had, for example, 2 statements in your code that both try to set the same wire. Why? Now I call this a wire. It's a wire. It's a net in the sense of a circuit design, and it's a voltage potential inside your design. But inside your SystemVerilog, it looks like a variable, and it's very easy, obviously, to double assign a variable. I mean, because you guys do it all the time, and like in a normal programming language, you always, unless you're doing single static assignment, it's very common to assign a variable twice on 2 different lines of code, but if you do that in Verilog, it's bad. So in this case, I've got these 2 inverters are potentially trying to set this wire to 2 different values. Okay, so that'll come up as an X. Another thing you'll see is Z. Z stands for floating. That's the value that the simulator will assign to a signal that is not being driven by anything. So essentially, every signal, every variable in your design has to be driven by one and exactly one entity or one circuit. If it's not driven by any, it will become a Z, which means high impedance. So again, in reality, if this happens and you were to probe a signal, a high impedance signal with, like, say, a voltmeter, it would be, you would probably be some, voltage between ground and the supply. But it would have high impedance to both because it's disconnected. It's just floating. It's not connected. No one's driving it. No one's setting it to anything. Sometimes, now, you can actually set a signal inside your code to Z. You can also set a signal in your code to X, but that doesn't mean you're deliberately double driving it. It means that you're setting it to don't care. If you set a signal to X in your code, it means the context of that is a don't care. But you can also set a signal to Z which can happen if you're trying to build a tri-state buffer. So if you want to have a case where you want to double drive a line, you want to have two different drivers, but you'll use these tri-state buffers to disconnect all but one at a time. And of course, if they're all disconnected, you'll have Z. Now we're not going to be doing that in this class. We're not creating any buses like this one where you can have multiple masters on a bus in Verilog. We're not going to do that. However, you will see Z still come up in your design. For example, if you have when you build your FPGA design, you may have a test bench and you forget to drive an input into the test bench, and you'll see Z there, and you're like, what's going on here? It just means it's not driven. You forgot to set it to something, or somebody didn't set it to something, or it got disconnected, or you have a bug in your code where you got the name wrong. You called it Y temp in this part, and you called it Y2 in this part of your code, and you meant for them to be the same, and they weren't. They have different names, and thus they're disconnected. All the connections are done through names inside of a module. Okay, so the wires are all, like I said, it's a name. Similar to the way the SPICE does it, if you guys remember that from your electrical class. Okay, so one difference, by the way, between SPICE is a circuit simulator, so SPICE isn't doing an analog simulation, whereas the difference is in Verilog, you're doing just a purely behavioral binary simulation. As a result, SPICE is much faster, but you're not able to put analog modules in there. You can't put a capacitor or a resistor inside your SystemVerilog, because SystemVerilog is only for behavioral, logic behavior. Okay, so so we talked about that. Now let me come back here and just give you a little bit more background. This isn't critical for you to know this for this course, but this is something that you may want to talk about when you're being interviewed for a job, and you want to know what you're talking about, some of the background stuff. So I mentioned there's two leading HDLs. Again, HDL is hardware description language. Some people call it RTL, register transfer language, but that refers to the same thing. It's basically it's a high-level language that you use to design digital logic behavior and structure. There's VHDL and Verilog. These are both very old. Although, I guess you could argue that, we're teaching C++, that's also an old language. But VHDL was the first one. It stands for VISIC, Hardware Description Language, and VISIC is also an acronym for Very High-Speed Integrated Circuit. The history of this is kind of fascinating, though. So it actually came out of the Department of Defense. The U.S. military was, they order a lot of custom hardware, custom chips, like single-use chips, or at least they used to. There wasn't a lot of off-the-shelf stuff back in the day. So, they would contract with a company to build an integrated circuit that's specific to some platform. And the problem is that they found that there was no concise way to specify how that thing is supposed to work. They would basically have to write it out in English prose. They'd have to say, well, it's got 16 pins, and one pin is a clock, and the other pin is an enable, and then you got 3 pins, and you'll drive a signal, and we expect the output to be the sum of this and that. Very imprecise, right? So, and not only that, obviously using English prose to describe the behavior of a chip is, there's a lot of potential for there to be misinterpretation. And then not only that, but when the chip comes back, there's no way to validate it. There's no automated way to make sure that it's working right, because it's all based on English prose. So they came up with VHDL as a way to formalize the way to describe the chip. So VHDL was originally just a specification language. It was like, here, go. You'd give it to the defense contractor and you say, build a chip that does this. And when I say this, I mean it should behave as this VHDL program. And then soon after that, they came up with simulators where you can simulate the behavior. And then eventually they came up with the synthesizers, which allows you to just take that program and convert it straight into hardware. And that's what we're going to be doing in this class. But those came later. So VHDL was originally 1981. Now the problem with VHDL, and I used to teach that in this course, and I switched. The main reason was because I started working more with industry, and I found that most industrial places use Verilog. VHDL is still used a lot in academia, but unless you're going to like grad school or something, if you're going into industry, chances are that you'll be using Verilog. The other reason is that VHDL, if you guys were to see it, you wouldn't like it because it's based on it comes from a lineage of languages that includes Ada and Pascal. And it looks weird. And the reason it looks weird is because it's very verbose. Like if you want to have an array, you actually have to type out array. If you want to declare a function, you type out function. There's a lot of typing involved. And that's because it was designed to be self-documenting. It was designed to be so verbose that you don't have to put comments in it. You can just read the code and figure out what's going on. But there's a lot of typing involved. And it's like, case insensitive. It looks strange. Whereas Verilog, which actually came out of industry, it came out of this company called Gateway Design Automation, which is eventually, they were bought by Synopsys. Verilog is closer to, it looks more like Python or Java, C. It's case sensitive. It's more sparse. It relies more on comments because if you don't comment it, it's harder to read. It's not self-documenting. So I think everyone should be more comfortable. But once you learn one, it's not hard to learn the other because they both have the same kind of semantics. They just have a different syntax. That's all. And the other neat thing about those two guys is that I could take a VHDL module and I can take a Verilog module and I can literally just plug them together and simulate them together or synthesize them together because the synthesizers and the simulators don't care which one you use. So they're interoperable. Okay, so I already mentioned the difference between simulation and synthesis. So in this class, what we hope you do, but not many of you are going to do this, I know from experience, we hope you're going to write your code and then simulate it, right? And then make sure it works. And when you're satisfied it works, then you're going to synthesize it and put it on the FPGA and actually get to interact with it as a tangible piece of hardware, right? If you don't do that, if you go straight from code to FPGA, there's a big problem there because it's very hard to debug and diagnose errors. And also it takes a long time to synthesize and put on the FPGA, so it slows you down. So now you might say, well, why would anyone not simulate? Well, okay, there's a problem. So you guys, I notice in this class, students will generally, they get into a habit that they prefer. They like to write the code and they like to go straight to the FPGA, or they might just go to simulation and they don't want to use the FPGA at all. Everyone gets into kind of a habit, but I encourage you to learn, both design flows, the simulation and the synthesis design flow, right? The pathway. They have different paths and different compilers that lead you to different things. In one case, you're basically testing, and the other one is you're actually building it. Now, the reason why you might be anxious to go to the FPGA, though, is that it's more tactile. In this class, our designs are going to be interactive. We're building you hit the switches and it lights the lights, and it's actual hardware. So, and some people are focused on end results. So, that's another reason why you might want to just go straight to the simulation or synthesis. But we're going to try to teach both in this class. Yes?
When you say simulation, do you mean model sim? Or?
Yeah, model sim, exactly. Yeah, we're going to use model sim as a simulator. Yeah, so we're using two separate tools. We have model sim, which is the simulator. And basically the idea is that you compile your code, you open it in model sim, and then model sim is a discrete event simulator. It allows you to basically view the running of your code as if you were looking at it on a scope, on an oscilloscope, or technically a logic analyzer, right, on the bench, right? So it's like a virtual logic analyzer. But synthesis, we're going to use a totally separate program from a totally separate company called Quartus. And so you might notice, and a lot of people notice in this class, they'll run everything through model sim and it's fine. And then they compile the same code written in the same language in Quartus, and all of a sudden Quartus has a problem with it. It's got a syntax error. It's like, well, it worked with model sim, why does it not work? Yeah, they're different parsers. There are slightly different interpretation. They interpret the language slightly differently. So even though in theory, anything that you write that works in model sim should work in Quartus on the FPGA, but you'll find that that's unfortunately not always the case. Sometimes you have to make some tweaks. Model sim lets you get away with more than Quartus because Quartus has got its actual real hardware, so it's less forgiving. It's not virtual, it's real. You're actually programming the FPGA. Okay, so we're going to try to teach both. Hopefully we can devote the correct amount of attention on both approaches. Okay, so we have this notion of a module. I've been talking about hierarchy, regularity, and abstraction. All of that is kind of conceptualized in the module. This is the most important concept in HDL. Actually, in VHDL they call it an entity. In SystemVerilog it's a module, but it's the same thing. It's basically a logic circuit where you have inputs and outputs defined at the top, and then the behavior defined in the middle. I mentioned there's behavioral and structural modules, or you can even mix them together if you want to. So basically, the first thing you define with a module is usually is the inputs and outputs, the module line. And usually you put one module per file. I mentioned that earlier. You don't have to do that, but everyone I know that does HDL programming does it that way. So here's an example. Now I want to point out a few things here that's weird about this syntax. So the file starts out by saying module example, and then open parenthesis, input logic A, B, C, output logic Y. Okay, so first of all, the white space and the white space is ignored like it is in Java and Python. So you'll notice that I have a new line there that I break up the module line into 2 lines of code. And I did that in my case to separate the inputs and the outputs. Some people like to to break it out even further and have one input or output per line. Yeah, it looks nicer, it's easier to read. I didn't do that. Now the other thing you'll notice is, well, wait a second, if A is the input and Y is the output, then what the heck are A and B, or B and C, rather? I didn't say what B and these two guys, I didn't say what B and C were. And that's because Verilog has this kind of a shorthand where if you have a type and then you specify multiple symbols after that type declaration separated by commas, each one of those will inherit. So obviously A, B, and C are inputs, right? Because I needed to make Y an output, I had to then break up that sequence of A, B, C and create another type, output logic Y, right? Okay, so then notice too that there's a semicolon, and I point this out because that's weird that you'd have a semicolon after that module line. That doesn't look like Java, right? They put a semicolon there that basically ends the module line but begins the module. So you would expect there to be like a curly brace there or something, but no, or a begin like you have in VHDL. No, you just, or colon like in Python. Yeah, they put a semicolon. I don't know why it does it that way, but you have to get used to that. And then the end module, which obviously ends the module, no semicolon after that. So you just have to get used to that. Yes.
Maybe it's because engineers are lazy, and so instead of a colon doing shift colon, they just did semicolon just to make it simple.
Yeah, so don't have to hit the one less key to hit. Yeah, it could be, but I don't know. It's weird they didn't put one after end module.
But pressing one more key is not the big price to pay for code you like to see.
Yeah, I don't know what the explanation was. It might have been a parser related thing. But anyway, so now this code this is the thing that is very hard. I find this part to be hard to explain. So I've got one line of code in there. It says assign Y, and then there's a Boolean logic expression there. This is obviously behavioral. This is purely behavioral code because I just assign a Boolean logic expression to Y. Now the thing about this that is so hard to explain is that assign statement represents an independent circuit that gets generated when you synthesize this. Okay. Now it may not get generated. You may not have exactly the same number of gates as operators. It may optimize it, right? Like you guys did in 2.11. It could optimize the logic, or ultimately on an FPGA, it actually just converts the whole damn thing to a lookup table anyway. It doesn't actually have gates, right? But that line of code represents a circuit. So if I were to put another line below that, I can't drive Y. Because if I do that, I'll end up with contention. So this line of code owns Y. You can't assign Y on any other line of code because that line represents a discrete circuit in the module, right? Now also, if I had another assign statement under that, it wouldn't matter what order they appeared in the code because they're just both concurrent circuits, right, that operate concurrently. They operate at the same time. So the way this works is anytime when you have an assign statement, there's a left-hand side and a right-hand side like you have in any other language. The right-hand side are the inputs to that logic circuit that gets generated, and the left-hand side is the output, right? So anytime any of the inputs change, the output will be updated right away, right? And so there's this linkage between the inputs and the outputs. When you simulate this, this becomes a discrete event. This gets simulated in a discrete event simulator. And in a discrete event simulator, it's event-based. So basically they say, every time that they tick the simulator, they have this list of signals which are triggered by certain events. And in this case, this line of code will be triggered when any of the things on the right-hand side, which is A, B, and C, anytime any one of those changes, the simulator will trigger that event and update Y as a response. Now, it may not change Y, because there might be a change in one of its inputs that don't cause the output to change, but it's still going to do that. So, for example, if you had a circular dependency in here, like if one of the inputs was also the output, and so you ended up with a cycle where I changed something here, changes, causes a change here, which then triggers that, which then update that, and then triggers that and updates that. You end up with what ends up happening is the simulator will literally freeze. Model sim will freeze. And the problem with that is you'll have no idea why, because it's hard to track those down. Yeah, hold on one second. You had a question? Did you have a question first?
So if you don't assign anything to Y, will this be like a high impedance or?
Yeah, if you don't assign Y, it'll be high impedance, right? Because unless something else was, well, it's an output of this module. So yeah, if I didn't assign it, it would be high impedance. That's right. Yes?
What about variables, when they can serve as input and output?
An input-output variable?
Yeah, or for example, variables, for example, modules with memory.
Mm-hmm.
If they have memory, they might be trigger itself and like end up.
Yeah, if there's like a cycle that breaks it up. Yeah, you're right. You can have, like if you have a register, you can have a circular dependency there because that register because there's memory involved, right? But yeah, in this case, I'm only talking about combinational logic. When we get to memory, I'll explain that it's the event that triggers it is actually the clock and not the inputs. But because this is combinational logic, anytime one of the inputs changes, it'll trigger that output right away. So if you guys ever running a simulation and it just stops and hangs, chances are you have some kind of a circular dependency in there. And unfortunately, those are real tricky to track down. Usually it involves you just having to comment out part of your code to try to track it down by trial and error. Yes?
Like Y equals not Y?
Yeah, exactly. Yeah, that. Y equals not Y. That alone would, that would hang the simulator. Yeah. It's weird too because in VHDL, if you do that, it'll say iteration limit reach, at least in model sim. Like it'll figure out in the code, the simulator, like, yeah, something's wrong here. I've been spinning on this for too long. The simulation doesn't converge. But for whatever reason, in Verilog, when you do it, it just hangs. I don't know, it might be a weird thing in model sim, limitation to model sim. Okay, but speaking of simulation, so when you simulate this, what do you actually see? Because obviously there's no print statements in there. There's no graphics involved. There's no console, right? What are you actually looking for? Well, generally speaking, the simulators are going to put out, as I mentioned earlier, they put out this kind of a timing diagram, which is meant to look like a scope, an oscilloscope. So the horizontal axis here is time. So you notice that it starts at 0 nanoseconds and we go up to 800 nanoseconds, right? So you have this flow of time, and it's kind of nice because you notice this blue line, that's your cursor. And so if you move that blue line, usually just by clicking somewhere, it'll put that line there, and then you'll see whatever the values were at that point in time where the line intersects them, they'll be shown here. So it's like you can say, I want to know what was going on at exactly 160 nanoseconds. So you click that, and you'll see the values there. So that using that cursor is a way to kind of find what the signals were, what the state of the signals were at a moment in time. So what's happening here is that you'll notice that these are square waves, obviously, right? They're binary, they're square waves. And because this is not an analog, if this were SPICE, they wouldn't be a square wave. There would be a, you'd see a curve there, right? But this is not SPICE. It's just a behavioral logic simulation. You don't want to simulate this stuff in SPICE. It takes way too long, if you can help it anyway. Yes?
The cursor does not correspond to the values. Like it should be like 0, 1, 1, 1.
Yeah, well, I don't know. I got this figure from the book. I don't know what was, that's a good point, is that I think the reason what was happening here is this cursor was off the edge of the screen or something, and it defaulted to 0, but that's a good observation. Yeah, technically it should be 1, 1, 1, 0, yeah, for Y. I don't even know for sure if that is the cursor. That's just how I interpreted this figure. I think that, because that's what the cursor usually looks like. Anyway, yeah, so you see that these are all square waves, and you see that A is 0, 0 meaning it's low for half the time, and then it's high for half the time, and then B is low for a quarter of the time, high for a quarter, low for a quarter, high for a quarter, and then C is low for an eighth, high for an eighth, low for an eighth, high for an eighth, low for an eighth. So what's happening is that the A, B, and C are being driven by an unknown entity here. Someone's setting A, B, and C, because I'm not setting it in this module. Some outside force is setting A, B, and C. Now this could be a script that you write in ModelSim, or it can be a test bench that forms the outer part of the circuit, the top level, right? We don't know who's driving these, but what's happening is that somebody is stimulating these inputs, and they're creating a counting sequence. They're going through every permutation of A, B, and C. Right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So basically it's counting from 0 to 7 essentially in binary, right? And then you're looking at Y. Y is reflecting what those true and false values would be evaluated to in that expression for each one of those inputs. So now obviously that's not practical to do this if you have a lot of inputs, because the number is going to blow up exponentially as we add more input bits. But if you have a small design like this, you can actually exhaustively brute force test every possible input value, right? Which is what's happening here. Normally you can't do that, especially if these are sequential circuits where time is also kind of an input as well. So usually you have to pick and choose how you stimulate the inputs to expose different test cases, which test vectors are called. But basically the point here is that we're going through all the A, B, and C's, and then we're looking at the corresponding Y. So you could literally just translate this into an 8-row truth table if you wanted to. But in fact, it's basically a truth table. It's just being shown horizontally like this instead of vertically like a truth table would, right? So it's basically a corner turn. It's a transpose of a truth table. But that's the way that these simulators will present results. Now ideally, and I'll talk about this more soon, ideally you won't have to look at these timing diagrams very often, because we're going to teach you how to write test benches that will basically exercise the inputs and then compare the outputs to what is expected to be on the output, right? And if they don't match, then it will raise an error. Hopefully, you'll run your test bench, there'll be no errors reported, and you're done. Your design, you can assume that your design works. However, if there is an error, or if you don't want to write a test bench and you just want to test this, by yourself in an ad hoc way, then you're going to be looking at these timing diagrams. So you have to get used to reading these timing diagrams. There's going to be a lot of these in this course. You're going to be, like when you run your CPU, you're going to be seeing, like for example, you'll have a line for your program counter, and your program counter will be incrementing. And then you'll see a line for instruction, and the instructions will be coming in. So you'll actually see literally the stream of instructions coming out of your instruction memory will be shown from left to right on this timing diagram. And then below that, you'll have your control signals, right? You'll have your ALU op code, and you'll have your reg write signal. So you'll see, oh, the reg write goes high there. I must be writing a register, whatever that instruction is. So you can put your cursor there and see what's going on, right? Likewise, the first CPU we implement will be comprised entirely of R-type instructions, which always write the register, right? So in that case, you'll see, you'll look at this and you better see a flat line for the reg write. You better see it writing every cycle, right? And then once we add the branch instructions, you'll see PC source, which is a control signal that changes the program counter, decides where to go next. And you'll see that one will only very infrequently pop up because it corresponds to the branch instructions that are executed and taken, right? So that's the kind of, that just gives you a preview of what to expect. And then this is another screenshot from the book, but this actually came out of the Quartus tool that we're using. And this is fascinating to me because it's really cool how it takes, and in this case it's not that big of a deal because it's just binary Boolean logic, but in general, yeah, you're going to be taking this code and it's going to get compiled not in a machine code as your like C would, but it's compiled into this. This is actually the output of the compiler. It's a gate level netlist. And you might notice, wait a second, hold on here. 1, 2, 3, 4, 5, 6. There should be 6 AND gates in there. I only see 2. Yes?
Pick the simplest possible number of logic gates.
Right, it minimized it. That's right, yeah.
Yeah, while you were talking, I was kind of working it out. I have it right here.
Yep.
The simplest number.
So it minimized it. Now you may get different results though. You don't know how it's going to minimize it. Generally speaking, I found that the synthesizer usually doesn't spend a whole lot of time. And when I say that, I base it on how long I have to wait. Like when you compile, usually the synthesis is pretty quick. Like it goes from that to that fast. Then it goes to put the design on the FPGA, and then you have to wait. That's a harder problem. Figuring out where to put those on the FPGA, that takes longer. Now the good news is that we have specifically chosen this FPGA and the tools that we use to make it as fast as possible. So there's these 2 companies that make FPGAs. The other company, Xilinx, their tools are a lot slower. And even though I wanted to use Xilinx FPGAs, it's not practical to do it in this class because it could take the whole lab just to do one compile, believe it or not. Whereas these guys are pretty fast. They're like 5 minutes at, I think the longest you'll wait is maybe 5 minutes. But it does take some time to do that. It's not instant. Okay, so now let me switch gears again a little bit and talk about SystemVerilog syntax. So I'm going to try to get through as much of this as I can so you guys can start using this in the lab on Wednesday and Thursday. So it's case sensitive. You might say every language is case sensitive. No, VHDL, the reason I mention that is because VHDL is not. Names can't start with numbers. Well, who would ever name something that started with a number? Well, in hardware you might, because a 2-input mux, you might want to call a 2 mux, right? So it makes sense in hardware, but you got to stay away from that. You call it mux 2 or something. White space is ignored. Comments use the same comments are the same style as in C and C++ and Java. Okay, so now let's talk about something else that tends to be a little hard to explain. So arguments. Okay, so modules, I emphasized this idea that modules are an important concept in HDL because everything is formed of connections of modules. The hierarchy is modules, the regularity is modules, the readability is modules. Everything is done through an expression of these modules. But the way that modules are connected are through their module lines. So as I mentioned, you have inputs and outputs. Now here's where things get a little weird though. So here are 2 modules. Normally they'd be in 2 separate files, but I'm showing them together here. Notice I've got one called and3 and I've got one called my design. My design is the top level module. And3 is the leaf module. Now you might say, how would you know that? Well, only by reading it, because it's not obvious. You have to look and say, oh, well, yeah, this thing doesn't have any IOs and it instances something and that one doesn't, right? So this is the top level and this is a leaf node. And so inside my design, I create no inputs and outputs here, but I have 3 logic signals that are internal values that are only inside this module. They're like temporaries, essentially. 4, yeah, A, B, C, and N1. And in the AND gate, I instance an AND gate. Now notice the syntax here is what you're familiar with from Java. You put the module name first, just like you would put the class name first if you were instancing an object in Java, and then you give it an instance name second. This instance name is basically meaningless, by the way, in your design. The only time you'll ever see this instance name is in the simulator. Inside the simulator, when you start searching for values, signals, you start drilling, it shows you the hierarchy, you'll see this. But the name is just basically for the simulator's sake. So this name is, essentially, you won't even refer to this name in your code because all of the interactions you do is through its IOs, right? So you will never actually type out this AND gate thing again. It's just, but anyway, I called it AND gate. So this is the module, that's the instance name. And then the way I connect it is I put a dot, and then I specify the port name, and then parentheses I put what I want to plug into that port from the perspective of this design, of my design, right? So I'm going to take, now first of all, notice they're out of order. That's okay. I'm going to connect Y first. Well, Y was the output. So the output of the AND gate, I'm going to connect to N1, which is N1. I don't know why I called it N1. B is going to be connected to B, A is connected to A, and C is connected to C. So what I want to point out here is that A, B, and C have the same name in here as they do in here. So when I simulate it, if I drill down inside of AND gate, the A in here will be the same as the A in there. It'll be just mirrors of one another, right? But the N1 in here will always be the same as the Y in here. So now I've got the same signal, but it goes by two different names, depending on what I'm looking at, right? It's one value here, one value in there, but it's still the same physical wire. They just have different names. So the problem is that if you go in and try to debug this on the FPGA, you use something called JTAG, and you can actually go inside of it and do a boundary scan and find signals in the hardware. The problem is that you don't know what it's called after it gets flattened, right? That same wire has two different names here, but remember, when you synthesize, it flattens it. It takes all this hierarchy out, and then it just gives it one name or the other, right? So then it becomes hard to figure out what that signal is in the actual hardware. So that's another reason why it's better to debug in simulation other than try to do it on the FPGA. Okay, so let me show you a better example here. I'm pretty proud of this. I've come up with this little graphical way to show this. So I've got three modules now. I've got AND3, inverter, and NAND3. NAND3 is the top. Those other two guys are internal. So my NAND3, I'm going to instance an AND gate, and then I'm going to drive the output of that. The output of that's going to be connected to the input of an inverter. And then the inputs to the AND gate will be connected to the top level inputs, as well as the output of the inverter will be connected to the top level output, right? So what I've created here with this module line is this black box. A, B, and C are my inputs, which are on the left. Y is the output, it's on the right, right? And then that's just, it's called NAND3, right? And now I can start filling it in. So the first thing I do inside this module is I instantiate an internal wire that's not visible externally, it's only inside, called N1. So boop, it's a wire, but it's not connected to anything yet. And then I instantiate the AND3, which creates that, and then through its port map, right, which uses this weird syntax, you've probably never seen this before. Maybe it's kind of similar to Python, but you're doing it where you're connecting, you're saying dot A is referring to the A on that A, whereas that A in the parentheses is referring to the A, the input for the NAND3, right? So through this port map, I am going to make connections there. So I've got my A's are connected, my B and C, but then remember, this is where this naming thing comes up. Y inside of the NAND is going to be the same signal as N1 inside the NAND3, right? Okay, just depends on where you're looking at it. And then likewise, the inverter, I'm going to connect A in the inverter to the N1 inside the NAND. Okay, so now I've got this wire, this net, has three different names depending on what you're looking at. In the simulator, you can traverse the hierarchy in the simulator, and you can put yourself into any of the scopes of these modules in the simulation. But you have to keep in mind that there's a lot of this renaming that goes on, right? So you have to, sometimes if you're in here, you want to look at Y, and if you're in the AND3, or sorry, if you're in the NAND3, you're looking at N1, whereas if you're in the AND3, you're looking at Y, but it's the same signal. And you can plot them both, and they'll always be the same thing in the waveform window. Okay, so, and there's, speaking of which, there's the waveform window. So this came from ModelSim, and I literally just did the same thing I did before, or not, the book had, I got the other figures from the book, but it went through a counting sequence. So I went through the same counting sequence. Now you'll notice that the most significant bit, A, actually goes through about 2.5 periods. So I actually run through the counting sequence like 2.5 times here. But you'll notice that Y is only 0 under when A, B, and C are 1, 1, 1, which Makes sense. That's what an AND gate does, right? And so there's my simulation, a little redundant. I ran it a little too long. And you can see the cursor there, and you can see the corresponding values there. Sometimes you'll see Verilog marks this as a strong one. And these are not strong. I don't know. I never figured that out. I don't know what this distinction there is. But clearly it's a 1, right? Yes?
Maybe it's when you have pulling up and having direct output. For example, if the wire is big 0, it's connected to the ground. But if you pull it up, it becomes strong 1.
Yeah, it's possible. I mean, the distinction is these were generated through tickle commands in the simulator, whereas this was generated through the module. So that's the difference. But yes.
So I have actually read the Verilog spec, and there are, I think, 13 different possible voltage levels, including the ones that you talked about earlier that are like tri-stated or don't cares.
Mm-hmm.
So they actually have like, I think, 5 different strength levels, and that is one of them. As far as we're concerned, though, it's just 0 or 1 or don't care.
Yeah. The point is, don't get too concerned about that.
It's not a problem.
Okay, so now let's talk about some. Let's talk about some multi-bit signals. So obviously, your designs will not all be single bits. You know, you're going to have program counter is going to be 10 bits. Your instructions is going to be 32 bits. Your registers are 32 bits. Your control values will be different widths, right? So can you have multi-bit signals? Yes, but this is weird. This is a strange syntax, the way they declare these guys. So notice I've got a module here with 2 inputs, A and B, and they're declared as input logic 3:0. Okay, there's 2 problems with this. Number 1, why 3:0? Obviously that's meant to represent a 4-bit signal, right? But in any other language, you would just say 4. You'd say it's 4 bits. Why the range? Why does it have to be 3:0? Well, that's just how you do it. That's the syntax. But the bigger problem here is, even bigger than that, in my opinion, is the fact that that number of bits comes before the name. If this were C, you would put the size of the array after the name, not before. So, and you know, it's funny. Every time I take a break, if it's been a while since I've written Verilog and I go back to writing it, I will always put that. I always make the mistake of putting that after the name, right? Yes.
Maybe it's just kind of similar thing like we put star in the C to define that this is a pointer. So this is similar to that star notation, and maybe that is also used because if you put it before the name, you can have several names, and you define that all of them are like 3 to 0.
Yeah, well, that's one advantage, sure. Yeah, and that's what's happening here. B inherits that same width. Yeah, and I think that's probably the rationale, I would imagine. Yeah. So anyway, yeah. So those are 4 bits, but of course you have to keep in mind too that if you're thinking in your head, I want these to be 4 bits, you have to internally subtract 1 to get 3, and then :0 because the 0 is inclusive. It's 3, 2, 1, 0. So every time you declare a signal with n bits, you got to subtract 1 from n to put in the code, which is obnoxious, but that's what they require you to do. It would be much more efficient just to say 4, right? Because that's what I want, 4 bits. So these are all 4 bits. I'm doing bitwise operators. Notice here I've got 5 outputs from this, so I'm starting to ramp up the complexity here a little bit because I now have 5 outputs on one module. It's fine. And they're using bitwise operations. Notice the operations. I didn't really harp on this too much, but these operators are the same operators you have in the languages you already know, right? So obviously OR is a bar. There's a complement, which is a tilde, which is a little strange, but that's the same as a bitwise inversion, I think, in C and Java. Ampersand is and, XOR is caret. So I think you guys, I don't think any of you would, I think you're all comfortable with that. So yeah, that's pretty much it. And then notice I see that each value now has, instead of being just high or low in the waveform, remember before it was just up or down. Now it's like, now it's like every time there's a change, there's a cross. And then the binary value is shown. And of course, you can show these as hex or octal or binary or decimal, however you want to show them on here. But the values are just put right there on the waveform. That's the point. Okay. Okay, so then there's something else I want to show you that this is something that you've got in Java and C. It's the ternary statement. It's this question mark syntax. I don't know if you guys ever use this. It's not as common, in my opinion, it's not as commonly used in C as it is in Verilog. In Verilog, it's used a lot. Not because people are trying to be fancy, but because it's a very natural way to create a multiplexer. So even though you can do this in C and Java, basically no one uses it. But in Java, there's a lot. You'll see this a lot because if you want to create a multiplexer, and multiplexers are everywhere in a CPU because that's the way that you create data paths. That's the fundamental way you steer data in your CPU is through multiplexers. So you're going to have lots and lots of these in your design. But it's nice because with this ternary operator, you can basically do it in one line of code. You can say assign y equals s question mark, that's the condition. So that corresponds to the select input on the multiplexer, if you guys remember the multiplexers from 211. And then you can say d1 if s is true, colon d0 is what you get if s is false. So basically what this is doing is allowing you to select you're driving y with either d1 or d0 based on the value of s, right? Now in VHDL, there is a more natural way to do this. It's called the when statement. But in Verilog, people use this conditional to do the VHDL when statement. But yeah, so that's essentially what's happening there. You just that's how you create a mux in one line of code. Now you might say, wait a second, I thought you said this thing should be hierarchical. So, well, actually, I guess I answer my own question. This whole module is just a mux. But the question is, would you actually create a module for the mux? Probably not. This is where you take it too far, right? If you take the hierarchy too far. In practice, if you want to put a mux in your code, you usually just put that line in there. You don't actually instantiate a mux module. Although that's what they did here. They created a mux module. But now it's like you're talking about a module with one line of code. That's a bit much. It's usually you inline that code normally, right? Normally it would be inline, meaning you would just copy it into your code. Okay, and internal signals. So I showed you this already, but just to reiterate, you can have internal signals, and in fact you will. So internal signals are kind of like local variables, right, in a method call. You declare them, and they represent internal wires, and they're used, and you need them to connect stuff. You have to have these things. If you have two modules you want to connect, you got to create an internal signal to create them. You don't have a choice. And so what's happening here is that I basically this is creating a full adder. So I'm going to assign, let's see, what do I got here? So this is a full adder where I also have a propagate and a generate signal, which is used for a carry look ahead adder. And I'll talk more about that a little later in the course. But basically, I'm going to create this P and G, which are declared and then assigned, and then I can use those to evaluate S and C out, right? Now, I mentioned earlier, use those to the connect modules. Obviously, in this case, I'm not using the connect modules. They're used as intermediates for these assigns. But keep in mind, though, that this creates an event chain when you do this, because if I change the state of A or B, that will trigger this statement. And if this statement's triggered, it will subsequently trigger this statement, because if A or B changes, P is updated, but if P is updated, it's on the right-hand side of this line of code, which will then cause a trigger of S, right? So this is causing, you can see how it creates this a chain of events through these intermediate variables. Okay, let's see, how are we doing here? 2 minutes left. Okay, so So this slide is here as a reference because you guys may want to refer to this. I look at it a lot because whenever I need to know what the order of operations, the precedence. So these are most of the operators. I don't think it's all of them. All the ones that you're going to use. Yes?
Well, one of teachers told that parent has the best precedence operator. Like you always well, most of the time know what to put in a parenthesis.
Oh yeah. Of course, you can still use parentheses. Yeah, absolutely. But if you don't have them, it follows this order of operations. So you've got not, multiply, divide, and mod. Now here's the problem. These guys, you have to be careful with those because a lot happens with a multiply. So when you use a multiply operation and you synthesize it, you're counting on the synthesizer to create the multiplier for you. Usually that's not how it works. Usually a multiplier is something that you would design. You wouldn't leave that up to the synthesizer. Add and subtract, though, is usually okay. You can use those. Shift, arithmetic shift, comparison. Now, this is a little weird, too, because I mentioned to you that Verilog doesn't really have types other than bit vector, or what they call logic, right? But a multiply cares about type. So if you multiply something by a negative number, it's different from multiplying it by a positive number, right? So that's where things get a little strange. Sometimes you have to introduce, when you do this, and we'll do this in our ALU, you have to say whether there's a special function that you have to use to specify whether the operands of these things are signed or unsigned. To be a little careful. Same thing goes for the comparison operations. So when I said there's no types, it's true, but sometimes you do have to specify signed, when you do these operations. So keep that in mind.
Just like in assembly language, you also can have like signed and unsigned.
Right. Yeah, but you can't declare them as signed or unsigned, is my point. You have to actually specify that when you do the operation. Okay, I think we're out of time. So if you have any questions, let us know. We'll see you in lab on Wednesday and Thursday. The lab is assigned, but you have till October 3rd. The TAs will give you more information about that in lab, and then I think you have enough information to get started. And then we'll continue with this on next week.